Hi, welcome back. This time I'd like to talk about how you use Mathematica to create the plots of some polar functions. So let's remember that when we're plotting one function as one variable as a function of another, like y is equal to x squared, often we'll write something like plot x squared, where x goes from -5 to 5, and then we get a plot of this function from here to here. Now, unlike in Desmos, if we were to type in plot theta squared, where theta goes from -5 to 5, Mathematica sees this as just some variable. It doesn't care that this is like r and theta. It just says this is a variable, and when I'm plotting something, I just will always use this as that variable axis. So if you want to plot something but use a polar coordinates, then you have to use polar plot. And when you use polar plot, then it will specify, oh, you want to do a polar plot of the function r is equal to theta squared. So here we see we can plot function r is equal to theta squared. We can plot the other functions that we've dealt with here. Remember, if you're using parametric equations, then you always, if you're using trigonometric equations, those are things that are already predefined in Mathematica, and you need to use capital letter to start. So 8 cosine of theta will give you this circle that's centered at 4, 0. If we wanted to plot multiple functions, we can put them both in the list here. So if we wanted to also plot sine of theta, we would get that circle here at the same time. And now you can see here we really do need to be careful about what our bounds are, because if I had just taken theta to go from 0 to 1, that's only give us part of this circle. So in Mathematica, you really need to know what the domain is of your function that you care about. For these circles, the cosine of theta, sine of theta, you can actually, the period is just pi. And again, you should put in capital pi, and that's going to give us the full circle. If we went up to 2 pi, it would give us the exact same circle. It would just go over it twice. So let's now look at this polar function that we talked about for 1 plus cosine of theta. This is a function that goes and makes this cardioid shape. And so you can play around with this. What happens if you put like cosine of 2 theta, cosine of 3 theta? You're going to get different shapes, and I suggest playing around with them, exploring what types of shapes you get in polar curves. And then if we look at polar plot of cosine of 4 theta over 3, this is the same thing we saw in Desmos, which is that this doesn't look like it's done, right? It doesn't look like we've visited all the points on the curve, and you can see that because the beginning doesn't match up with the end. And so that's telling us we need to know what the domain of this function is. So if we use a manipulate command, we could just see what happens as we expand this value. So let's let this be the end, and we're going to manipulate where end goes from 0 up to 10 pi. And so as we I'm going to start with 0.001 just so that we don't get any. So now as we expand our function and we see what happens as theta increases, we see that at some point our function comes back to where it started. And as we calculated in the previous video, this distance, the right value for how big this should be 6 pi. And so that gives us a graph of our polar function, r is equal to cosine of 4 theta over 3. All right, let's stop there. See you next time. Bye.